when a race car is flying down the track, we can kind of think of the space under it as a pipe for the air to go through. And you can see this part here is raised just a little bit. So the cross-sectional area of this space under the car at the very front is, say, 0.35 meters squared. But then it goes down a little bit, and the cross-sectional area by the time you get to the middle of the car is, let's say, 0.32 meters squared. And the question then is, what effect does that have on the car? Is it going to be pushed up or down, and but with how much pressure and with how much force? So let's start to address that. Well, what's going to happen to the speed of the air? If we know the air's, relative to the car, the air's going in at some velocity at the wide part, and as it gets narrower, there's less cross-sectional area, therefore the velocity must increase a little bit. So under the car, the air is going to have a higher velocity than before it gets to the car. So Bernoulli tells us that a high velocity of a fluid means a lower pressure for the fluid. And what's the result of that? Well, normal atmospheric pressure is going to be pushing down, and a little bit less than atmospheric pressure is going to be pushing up because of that lower pressure where there's a higher velocity of air fluid going under the car. So the net result is a little bit of pressure pushing down on the car. And I guess this is handy for better traction on the turns. And let's figure out exactly what that difference is. Let's figure out the actual pressure under the car. And for that we can use Bernoulli's equation, which can be written like this. Oh boy, that's a big equation. So what this is saying is the left hand is describing the first situation of the air before it gets under the car. So right here is everything on the left, and then everything on the right is after it gets under the car. So this is the pressure under the car, and that's what we want to find. We know that P1 is atmospheric pressure, which is about 100,000 pascals. Pascals is the SI unit for pressure. Now let's simplify this a little bit. This term here, the rho gy term, what that's there for is to take into account difference in height, difference in elevation of the pipe where fluid is flowing. So that y is the height of the pipe. But this, what we're saying is our pipe, our area under the car, it doesn't go up or down. So whatever y1 is, we'll probably say like it's 0, is the same as y2. So on both sides, we know this rho gy term is going to be the same. Assuming that the density is the same, the rho is the density, we're just going to assume that the density of the air doesn't change significantly as it gets sucked under the car. So if rho gy is the same on the left as it is on the right, we can just get rid of it on both sides. We can subtract rho gy from both sides. Alright, what else is in this equation? Velocities. Alright, so the velocity of the air right here as it hits the front of the car, and again this is the velocity of the air relative to the car. So that would just be whatever the car's velocity is, because we can imagine a situation where the air is just sitting there, there's no wind blowing, the air is just sitting there above the track, and the car zooms by at 100 meters per second, and to us in the car it looks like the air is going by at 100 meters per second. So that's just whatever the car's velocity is. Let's call it 100 meters per second. I think that's somewhat reasonable. It might be a little high if this car's making a turn, but it's an easy number. And then what do we know about V2? Well, we know that the air increases its speed just a little bit because the cross-sectional area decreases. Our pipe, as we call it, gets a little narrower, so the velocity must increase. So it's a little bit greater than 100 meters per second. And we're going to actually have to find what it is exactly. But we can do that using our equation and solving for V2. And let's put in some numbers. 100 meters per second times 0.35 meters squared over 0.31 meters squared. And that gives us 112.9 as the velocity of air under the car. We still don't know rho, which is the density of the air, but I have a feeling that it might cancel out because we are assuming that it doesn't change as the air goes under the car. So I'm going to take what's left of our equation up here and solve for, what do we want to solve? Oh yeah, P2, the pressure under the car. So here's what we got, solving for P2, and that can also be written like this. And it looks like we do need to find rho, the density of air. And I did just Google that, and the internet says that the density of air is about 1.25 kilograms per meter cubed. And our V1 was 100 meters per second, and the V1 gets squared, and our V2 was 112 meters per second, 112.9. And that gives us a pressure under the car of 99,280 Pascal. So here's what we know about the car now. We know that on top there's 101,000 pascals of air pressure from the atmosphere pushing down, and on the bottom there's almost the same amount, but a little less, 99,200 pushing up. But there is a net pressure here, small compared to the air pressure, but it's the difference between the two, which is 1,720 Pascal. That's the net result of Bernoulli's principle and the air going faster under the car. Let's translate this to a force. So we know that pressure is force over area, therefore force is pressure times area. So let's approximate the area of the top of the race car. Maybe if we're the air on top and we're pushing down on the car, we see about maybe 4 square meters of car, say, right? So our pressure is, the net pressure is 1,700 Pascal. Pascal, remember, is also Newton per meter squared. And that area we're approximating to be maybe 4 meters squared. So the force that results from this differential is, so our overall force is a lot of newtons. Let's see, how does this translate to pounds? Or kilograms, I guess would be easier to find. We know that the force in newtons equals the mass in kilograms times 9.8. Therefore the mass in kilograms equals the force, which is 6,800 newtons over the acceleration of gravity, 9.8. And that gives us about 700 kilograms. And there's about 2.2 pounds per kilogram, so that would be about 1,500 pounds of downforce on this race car. That's a lot. So that answer makes me a little uncomfortable. And I actually look back, and earlier when I said the area under the car was 0.32 meters squared, I actually used 0.31 meters squared in the problem. So that increased the magnitude of the answer. But that brings up an interesting point, that when the vehicle when its shocks go up or down, or gets closer or farther away from the ground, that really affects the magnitude of the downforce. And also, the speed of the car itself affects the downforce. So I picked a really high speed, 100 meters per second. That's over 200 miles an hour. So it would be a higher downforce at that high speed. And also, if you look at pictures of certain race cars, they have these kind of fins on the bottom of the car that have a much smaller area than 4 meters squared, probably. So maybe I even approximated an area that was too large. But the point is, you can get a lot of downforce and increase your traction by this effect. And I was just reading around online, and they were talking about some cars a while ago that really were able to utilize a lot of downforce, and they were able to just zoom through oil patches because there was they were able to get just so much more traction. So now let's think about this principle, but let's flip it around. So here was the kind of shape of the bottom of the car in the last example. What if we were to flip that shape around and make it like this, and have air go faster over the top instead of over the bottom? In that case, there would be a lower pressure on the top and a higher pressure on the bottom. And we saw that there could be a lot of net downward force because of a differential of air velocity on the top or bottom of an object. So there can be a lot of force, a lot of net force upwards on an object. And question, can there be enough force to actually lift that object off the ground? Well, yes. That's how an airplane works. So this is kind of a wing here, and the air has to travel further over the top of the wing than over the bottom, and the air that comes in at the same time here and here has to meet up at the same time at the end of the wing. So if this air on top has to travel farther, it has to go faster. And it's that differential in velocity that causes a differential in pressure that results in a net upward force on the wing. And that's the force that lifts a plane in the air. And one more thing before I go. A little story about some great scientists. Einstein, Newton, and Pascal. They all were in heaven, and they decided to play hide and seek. And Einstein closed his eyes. Newton and Pascal ran off, except Newton stopped after just 3 steps, and he drew a square on the ground with 1 meter on each side of the square, and he stood in the middle of it. And Einstein opened his eyes, and he saw Newton standing there, and he said, "Newton, I found you already. Why didn't you hide better?" And Newton said, it is not Newton you have found, but you have found a Newton on a square meter. Therefore you have found a Pascal. If you don't get that joke, go back and read more of this chapter. If you don't find it funny, yeah, you're probably right.